Okay, so let's look at this problem from Concepts of Physics by H.C. Verma, where we're talking about a block of mass m suspended by two springs on a horizontal frictionless surface, which is originally unstretched, and we need to find the speed when the block, after getting displaced by a distance x to the right hand side, as you see at position B now, is released, and then what is the speed of the block when it crosses through the mean position. Now, this seems like a relatively simpler problem in the topic, but it is important to discuss through some of the concepts we will use down the line in more complex problems. So as you would know already that whenever a spring is stretched by a distance x, the force that it exerts back to the body would be k times x, where k is the spring constant. If you talk about vectors and directions, then there would be a minus sign excuse me, to indicate that the force is in the opposite direction of the extension. Now, we also know that because of the extension or compression of the string, there is a potential energy which is stored, which is equal to half times kx square. How do we derive it? We can just simply talk through the work done by the spring. The force is F times x. We can take a small displacement of dx and then just integrate that to get this value of half kx square. Now, in this type of problems, you would often see that it's easiest to conserve the energy of the system. That's where you directly get the velocity or the speed terms for kinetic energy, and you know that there is potential energy in the system, which is denoted by the half kx square terms. So if you just conserve energy at the initial and the final state, it should give us a simple way to find the speed. Now, the block was stretched to the point B, at which point it was released. So let us take that as the initial state of the whole system, and we say that the energy at point B has two components, which is the kinetic energy, obviously zero at that point because the block was stretched at that point and it was about to be released, and then the potential energy would be, let's say this is initial, and then the potential energy would be the sum of the two individual energies because of the springs k1 and k2. So we could just say that it's half k1x square plus half k2x square. Now the extensions are the same for both the springs, so this is the expression for the energy. Now we could also think about what's the energy at the point A, or the mean position, where the body might be coming back. Say it comes back over to the center position and has a velocity v at that point, or the speed v. Now we can say that at that point the kinetic energy final has to be half mv square right? But there is no potential energy at this mean position because the spring is coming back to their original state, so it is all zero. Now what we can say is, with the conservation of energy, that at point B and point A, total energies should match, which means that half mv square should be equal to half x square k1 plus k2, which just implies that v square equal to k1 plus k2. You can just cancel out the 2 here, and we could say this is multiplied by x square, and there's a term of m over here, which implies that the speed of the body is root over k1 plus k2 divided by m, this whole multiplied by x. So we could just see that this final speed Depends on all the terms K1, K2, M, and the displacement it was given. So let me know if this seems interesting, and then we can talk about a more complex setup where the body of mass M is now a rolling sphere or a cylinder where the springs are attached on the top, and then because of the extension, the spring undergoes a rotation about its center. That'll be an interesting problem. Let me know if you're interested to go through that, and I can make a video. Great. So this is it for now, and I'll see you on the next one. Thank you.